Hi, today let's have a look at this vintage indicator. This is an exhaust gas temperature indicator which was used in a Boeing 727. The range is 0 to 850 degrees. This thing was manufactured by Amtech. There is a manufacturing date, 1981. You can see the part number of this indicator. The sensor should be a thermocouple, obviously. First, let's see what is inside, and after I will try to get it work. Okay, so we can see that this unit is not very complicated. There is a transformer here for the power supply. Okay, we can see there is this capacitor which was replaced. We can see, so this one is obviously a modern capacitor. It was not the original one. Okay, we can see here a servo motor. Okay, so there is a motor and a potentiometer, and we can see several electronic boards. We can see the interconnections between boards. It is interesting. It is possible to remove the boards without desoldering anything. We can see the mechanism here, transist coil. Okay, so we have 5 wires, 3 for the potentiometer and 2 for the torque motor. Here there is a resistance of 36 ohms. This is the torquer. And on the other side of the connector, we have the potentiometer with a total resistance of 27 kilo ohms. Okay, so 7.3 kilo ohms between these two contacts and 20.7 here. Okay, so this is the first board. Probably the servo control amplifier. You can see we have an op-amp here. You can recognize here the connection for the power supply. So this is a dual op-amp. And for sure, this is UA 747. Okay, we should have a push-pull output stage for the torquer. Okay, we can see here that the base of these two transistors are connected together, the emitters also, so this is the output stage. Okay, we can see that the base is connected here to one output of this dual op-amp here. This is this pin here. And we have the power supply between these two terminals. The torquer should be connected to that point. Okay, so let's see this board. On that board there is an IC UA 4136. That code 79. And there are two trimmers here. Okay, so this board is interesting, and we can see that the thermocouple is here. Okay, so white and yellow wires. So this is one more time a specific connector. Okay, we should have 2 pins here for the thermocouple with alumel and chromel alloy. And the cold junction is here inside, so this is a cold junction compensator. Inside we should have a thermistor which is close to the cold junction in order to measure the temperature of this cold junction. And here we should have the input stage of the thermocouple. So this should be a precision op-amp with a low offset drift. So I cannot read the complete reference. It is an LH00 something, 004. This is a metal foil resistor from Vichy. And there is another one here. And the last board is this one. So this is obviously the power supply board. And there are 2 bridge rectifiers here. And in the middle there is a classic 723. Okay, so first I will do the reverse engineering of this little board, the servo control board. And after I will do the reverse engineering of this one. So this one is a little bit obscure. And finally I will do the reverse engineering of the input stage of the thermocouple. And after that it will be possible to get it work. For the test I have connected this indicator to a thermocouple simulator DigiPod 5. The temperature is set to 0 degree. I will increase by step of 10 degrees for the moment. I will increase now the temperature by step of 100 degrees. Okay, the temperature is exactly 600 degrees. As you can see, this indicator works perfectly. This is a simplified schematic of a piecewise amplifier. The behavior of that circuit here in the middle depends on the polarity of the input voltage of this op-amp. If we assume that this voltage is negative, so therefore the output voltage will be positive here. In that case, this diode will be reversed biased. Therefore, there is no feedback, and this op-amp has no effect on the circuit. Okay, so we can remove this op-amp. In that case, we have a classic inverting amplifier. The gain is defined by all resistors of that circuit, and also the voltage depends on the voltage V1 here. But if we assume that the values of the resistors R3, R4, and R6 are much higher than the resistors R1 and R5 here, in that case, the gain of the complete circuit will be minus R2 divided by R1. Now, this is the first portion of the characteristic here. The threshold voltage here is minus V1 multiplied by R3 divided by R6. This is the limit of voltage V1 when the voltage is 0 on that point. Let's assume now that the voltage V1 is above this value here. In that case, the output voltage will be negative here. In that case, this diode will be forward biased. In that case, the negative voltage present on that point will provide a sink current regarding this op-amp here, a current flowing on that direction here. Okay, but here there is a current flowing on that direction. Therefore, the current flowing through R2 is below the current flowing through R1, so therefore the gain is decreased here. The problem is that the two gains here depend on the values of all resistors. So there is a much better approach, which is to add a diode here in the feedback. Therefore, on that part of the characteristic, when the voltage is positive, this diode provides a negative feedback. In that case, the voltage on that point is 0. We have also 0 volt on that point because we have a negative feedback. Okay, so in that case, the current is 0 here. So therefore, on the first part of the characteristic, we have only these two resistors, and the gain is really defined by the ratio minus R2 divided by R1 here. It is also possible to have a higher gain on that section of the characteristic. Okay, so something like that. In that case, we need to add an inverting amplifier between this point and the resistor here. Okay, something like that. In that case, on that part of the characteristic, this voltage is negative, but because of the inverting amplifier, we have a positive voltage here. So this permits to have a current on the same direction than this current here. This current permits to increase the current through R2 here, and this increases the output voltage here, and we have a characteristic like that. This is the complete schematic diagram of this EGT indicator. I drew this schematic after 2 days of reverse engineering. In the middle, we have the power supply. There is a transformer here with several secondaries. There are 2 bridge rectifiers. One is used for the generation of plus and minus 15 volts. The second one is used for the power stage of the servo control amplifier. Power supply input voltage is here. It is 115 volts, 400 Hz. There are 2 filtering capacitors connected to the mechanical ground. And this is a positive and negative reference voltage generator. It uses the classic LM723. The positive voltage reference is here. There is a very big capacitor here, 2200 microfarads. I don't know why the value is so high. And here there is an inverting amplifier which permits to generate a negative voltage reference. On the top of the screen, we have the main circuit. There are 2 different sections. There is the first section here on the left, which is the front end of the thermocouple. There is in the middle here a piecewise amplifier, and on the right we have the servo control amplifier. Let's have a look first at the front end amplifier. This is the front end amplifier. The thermocouple type K is here. So the connector is specific. These 2 pins have the same alloy than the thermocouple itself. Therefore, the cold junction is inside this module. Here we have the cold junction. This cold junction is compensated using a small voltage divider here, using an internal thermistor which measures the temperature of the cold junction. And there is an internal resistor and an external one. So therefore the voltage on that point is the sum of the thermocouple voltage itself plus the compensation voltage here, which depends on the temperature of the cold junction here. And this voltage is amplified using this amplifier LH0044. This is a precision op-amp with a small offset and a small offset drift also. The gain is defined by these 2 resistors. They are metal foil resistors, so therefore the ratio is very stable. The gain is approximately 76.2 exactly. On that point, there is a voltage which is approximately proportional to the temperature. This voltage is fed to a piecewise amplifier. This is the dial of this EGT indicator. We can see that we have 3 different scales. The first one is from 0 to 500 degrees. The second scale is from 500 degrees to 700 degrees. You can see that here 100 degrees has approximately 3 times the deviation of the first scale here, 0 to 100. And above 700 degrees, we have the same scale than the first one here. So this is the behavior of the internal amplifier we should have. From 0 to 500 degrees and between 700 degrees and 850, we have the same gain, which corresponds to this first scale and the last one here, and between 500 degrees and 700 degrees, there is here a gain, which is approximately 3 times this gain here. So this is the reason why there is a piecewise amplifier. It is that circuit here. As we have seen, there are 3 different gains on that circuit. The first one corresponds to this path here. Okay, so we can see that we have an inverting amplifier following with another one. On that point, there is a voltage which is proportional to the input voltage here, the out, which is the output of the first stage. So actually, on the current circuit, these diodes are not present. We can recognize here the basic circuit of the piecewise amplifier. We can notice that between 0 and 500 degrees, these resistors here have an effect on the gain of the first range, 0, 500 degrees. As explained before, there is a solution for that is to add a diode in the feedback here and another one here. In that case, between 0 and 500 degrees, there will be here a positive voltage, but thanks to this diode, which provides a negative feedback, the voltage here will be 0, but we have 0 also on that point, therefore no current will flow through this resistor, and it is the same for that circuit. So therefore, between 0 and 500 degrees, the only current is this one here, which flows through that line. Okay, so we have a voltage here, and we have this current is also null. Okay, so the gain of the first range doesn't depend on the values of all other resistors here. I don't understand why the designer didn't place these diodes here. It is much better because otherwise, when you adjust the gain of the second or the third range using these 2 trimmers here, there is an effect on the gain of the first range. So probably when you adjust these resistors, maybe you have to readjust the first range. The last circuit is the servo control amplifier, which is on the right here. The input voltage of the amplifier is here. The torqueur is here. The torqueur is linked mechanically to the feedback potentiometer. There is an error amplifier. The gain is 100 exactly. The error signal is here. It is the difference between the input voltage here and the feedback voltage. This error is amplified, and the amplified signal is fed to the torqueur. The torqueur will move the shaft until the difference voltage is null here.